Physics, Kinematics. In this video, I will show you how to move from a position time to a velocity time graph. Firstly, I will explain the three symbols that you need to know in order to move from a position time to a velocity time graph. There are two types of quantities, vector and scalar. A vector quantity is a quantity with both direction and magnitude. A scalar quantity, however, only has magnitude. Position is represented by the letter D with a line at top, which means that it is a vector quantity measured in meters. Velocity is also a vector quantity, and it is represented by the letter V with a line on top, and it is measured in meters per second. Time is a scalar quantity, and it is represented by the letter T, and is measured in seconds. To move from a position time graph to a velocity time graph, we will need to exploit the relationship between them, which is the slope. As you have learned in math, the slope of a line is y2 minus y1 over x2 minus x1. The slope in a position time graph is velocity, which is the difference in position over the difference in time. Let's go over an example. The first point is 1 meter north in the first second. In the fifth second, we have the second point, which is 5 meters north. All we have to do now is substitute the four different values on the graph into the equation above. As you can see, the second point is 5 meters north, whilst the first point is 1 meter north. So we subtract 1 from 5. Similarly, the second point is at 5 seconds, whilst the first point is at 1 second. So we subtract 1 from 5. This gives us a final answer of 1 meter per second north. Remember to put north in square brackets, as velocity is a vector quantity with direction. Here's what uniform motion, or in other words, constant velocity, looks like in a position time graph. Here's what it looks like in a velocity time graph. As you can see on the velocity time graph, the line is flat, which means that there is no change in velocity. Or in other words, uniform motion, as it is not speeding up or slowing down, it is staying the same. Now we're going to take a look at acceleration speeding up, which looks like a curved line in a position time graph. However, we will not try to calculate the slope of the curved line in the position time graph, due to the fact that calculus is needed to calculate the tangent. Despite the fact that we are not calculating the slope, note that the slope is increasing as we move down the line. Or in other words, the change in velocity is increasing. As such, the curved line in a position time graph is represented as a straight line of increasing magnitude in a velocity time graph. Acceleration slowing down is also a curved line in a position time graph. However, the difference is that the slope is decreasing to 0 as we move down the line. Now, let's convert the complex motion in the position time graph to a velocity time graph. Firstly, split the graph into different vertical sections based on when the type of motion changes, whether from uniform motion to accelerated motion or vice versa. Then, write out the equation, velocity equals the change in position over the change in time. Then we may begin on calculating the slope of each vertical section. As said previously, we will not calculate the slope of the curved line. However, we can estimate the slope, or rather, the change in slope in the position time graph. For section B, you can plot 2 points. The first point, which is 5 seconds in, is 2 meters north, whereas the second point, which is 6 meters in, is 1 meter north. All we have to do now is substitute those points into our equation and we get negative 1 meter per second. Note that I have chosen north as positive and south as negative. Therefore, our final answer is 1 meter per second south. Similar to section A, we will not calculate the slope for section C, but we can see that the change in slope is decreasing to 0. Much the same as section B, we can select 2 points in section D. The first point is 14 seconds in and is at negative 1 meter or 1 meter south. The second point is 17 seconds in and is at 0 meters. So we just substitute those numbers in, and our final answer is 0.3 meters per second north. So, to recap on how you convert a position time graph to a velocity time graph, you first split the graph into vertical sections. Then you find the slope for each vertical section. Thanks for watching.